Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Univa. We have the CTO of the company, Fritz Ferstl. Fritz, how are you doing today?
I am great, Rich. How are you?
Oh, I'm great. I'm getting over a little cold here, but I'm going to be ready for ISC when it comes. And anyway, Fritz, I thought we should catch up. There was some news yesterday about Univa working with a Formula One team in India called Sahara Force India. So I guess congratulations are in order.
Thank you.
Yeah, I mean, this is these teams, HPC's become a competitive weapon in Formula One, so this makes perfect sense to me.
Well, I am a avid Formula One fan, so I know everything about that, and specifically also the importance of HPC. You know, these guys can choose between doing HPC experiments or wind tunnel stuff.
Yeah.
And sometimes wind tunnel is the better investment, and HPC experiment is the better investment.
Yeah.
And that stuff is run on Grid Engine.
Well, yeah, and it makes sense. If you're going to be productive, you need a good system management software package. So we'll have to wait for more details on that. But in the meantime, we have a slide deck here, and I thought, why don't we go through that, and then we'll follow it with a Q&A.
Yep. Okay. So title of the talk is Rev Up Your HPC Engine. That actually was the title of the talk even before the news of yesterday, but it sort of fits. Now, as for slide number 2, this is my only slide where I will be talking about Grid Engine or Univa in this particular talk. I'm going to talk more about challenges in HPC systems and how they project to workload management in general, right, and what type of solutions you can apply and stuff like that. But my little boilerplate about Univa. So we call ourselves data center automation experts. We try to allow our customers to do more with less when it comes to big compute or big data. We sometimes say we help those organizations play a better game of Tetris, so putting workloads, where they best fit. We are based in Chicago, have lots of offices around the globe. We are now in the business we're currently in for about 3 years and have acquired more than 500 customers throughout those years, and most of them are actually Fortune 500 customers. You see a set of logos on the right-hand side, and they really go across all verticals, whether that's manufacturing or oil and gas or chip design or biotech, life sciences, or also transportation business, for instance. We have a number of customers in that market as well. In terms of products and technologies, we have 4 pillar products. One, the primary product certainly is Univa Grid Engine. Then Unisite, which is accounting, reporting, and analytics package, which sits on top of Univa Grid Engine. Then our license orchestrator product, which helps share licenses across clusters, for instance, or across projects and similar things. And then UniCloud, which allows you to deploy a cluster with everything configured readily, like Grid Engine, for instance. Deploy a cluster on a set of bare metal machines, on virtual machines, or on cloud nodes, or on mixes if you want to run a hybrid model, and then you can flex for instance, the size of the cluster, if that's something that you need to do. So that's the overview on Univa. Now really over to our talk on slide number 3. So what type of challenges for workload and resource management systems do I see in HPC these days? So on slide number 4, first of all and foremost, certainly scalability is always an issue, and it has been for the 20 years I'm in this business. What you see currently, if you go into a state-of-the-art HPC data center and you ask about growth numbers and stuff like this, then you will notice that the node counts often stay flat, or sometimes they even go down. The number of sockets pretty much stays flat usually, but the core counts explode. So what comes along with that is in particular that also the numbers of jobs that you can actually run in such a system explodes. So, and that also comes down to shorter runtimes, for instance, for those jobs. So there's just much more traffic on such a system, and that really puts a load and a strain on the workload management system. In large commercial sites, they currently approach or go beyond 100,000 nodes, cores. So that's what our biggest customers basically are. And then when you look at throughput clusters, they process more than 150 million jobs a month. You know, that's really a staggering amount, and the workload management system has to keep up with that. Another dimension is heterogeneity. So first of all, you have a lot of heterogeneity in the hardware. I mean, you have all those multi-socket systems, and each of those sockets has multiple cores. And then you do partial cluster upgrades. So it's not uncommon that in a single cluster you have several generations of chipsets and server architectures. And you have to manage all that, right? You have to make sure that jobs run on all of them, or that the right jobs run on where they are designated to run. With those different server architectures, of course, you have also evolution in the memory architecture, in the networking, in the storage systems, and you have to account to that as well. And then finally, nowadays, you also add accelerators into it, like NVIDIA GPUs or PHYs from Intel. And then, of course, you want to run something on that hardware, and what you want to run is also very diverse. So you have different types of job profiles, like, for instance, throughput jobs, which are usually small units and lots of them. Sometimes you can combine them into what we call an array job, where this is basically the same type of job crunching on a huge set of data, and it gets instantiated over and over and over again until all the data is digested. Or you have large parallel jobs which run for a longer time and consume a larger portion of the cluster. You may have interactive workloads or sessions, you know, where you have multiple things which are grouped together. Then you have reservations, you know, where you need to reserve parts of the cluster for some future project or something like that. You may have transactional workloads, like in the big data space. And then you have hybrids of all of that, where you combine those different things and you group them up in dependencies and workflows and all of that type of stuff. Yet another dimension is, I mean, you have all these different workloads, but of course you want to orchestrate them. You want to decide how the cluster is going to be used by them. And for that you have policies, and you actually have a lot of different policies. So for most, of course, you want to automate things. So those policies are usually automated, but immediately you get the challenge of transparency. So can I really be sure that what I have set forth in the policy is being implemented? And am I able to prove it to my users, for instance? Can I inspect it myself? You know, these types of things. At least in corner cases, you want to be able to do manual overrides. So that somehow has to be woven into the picture as well. You have policies that determine automatically the preferential access, like fair sharing and similar things that allow you to define priorities, that control reservations, that give jobs more priority, more urgency if they require very expensive resources, let's say like a super expensive license, which cannot, you know, sit idle. You have quotas which you want to manage. You have deadlines you want to manage. And really the trickiest part of all of that is those policies do not necessarily fall in step, so they often conflict. If I have, let's say, throughput jobs and large parallel jobs, they have very different policy requirements, and those conflicts need to be resolved somehow. Another angle to the picture is the variety of the different use cases which are implemented. I mean, if you just look at single jobs, I mean, the whole situation is easy. But if you look at what is the overarching operational model of a organization, then things get a little bit more complicated. So you could have, for instance, a classical HPC site, which largely does simulation. Let's say somebody like an oil and gas company would do that, or industrial manufacturing company. So you have large parallel jobs or many mid-sized parallel jobs, but not too many. In a verification or test scenario, like you have it in the chip design, you would have huge throughput clusters, where you run very small jobs, but lots and lots of them. And sometimes, as I mentioned before, you can group them up and move them into an array job if you do something like a parameter study. So that makes things more efficient. In some cases, for instance, in the financial services arena, we run more and more into ultra-short jobs, which may take much less than a few seconds. Big data and data mining has yet a different type of job profile. And then there's also a difference whether, for instance, you really want to use your nodes exclusively so each job really owns a node, or whether you have shared usage, because if you have shared usage, then you face a number of problems like one job stealing another job, the memory away, or similar things like that, and you have to have means to fence jobs and manage that type of conflict scenario. So finally, to conclude my list of challenges, and that's certainly not a final list, on slide number 8, I have the geographical distribution and clouds that we have nowadays, specifically in larger organizations or larger institutions. So if you have multiple clusters spread around the globe, then you definitely still want to be able to share at least some of the resources. And that's not only talking to servers, but also regarding licenses, for instance, or data, or other types of resources. If you share resources, then you have access latencies, obviously. So for data access, that's of course very, very pronounced. You have security issues, which you have to handle. You have file system dependencies. So before a job starts, the data needs to be there, and you have to do things like pre or post staging. And in general, the data locality needs to be managed. So you could, for instance, bring the job to the data or bring the data to the job. All those kinds of things play a role. So let me close with this list of challenges and now segue over to a few solutions or approaches or best practices that either we are working on as a workload management provider, or which customers can consider as part of their installation. So first of all, it's definitely yet another point in time where our type of software needs to evolve. I mean, software like Grid Engine, or Univa Grid Engine in particular, is over 20 years old. But that doesn't mean that this is yet still the same code that you're using, right? So the product has evolved in steps over time. And I think there is another step waiting for us right now, because the core count growth that we're seeing and the growth in the job throughputs that we need to manage definitely mandates a few core enhancements in some parts of the architecture to make that feasible. The same goes for scheduling algorithms. Specifically, the bigger the cluster grows, the more types of job mixes you see. And to handle those job mixes and the conflicts that arise from them efficiently, it's one of the things that you need to do is really improve some of the scheduling algorithms to be able to handle that. And the scheduling of ultra-short jobs is a particular challenge that wasn't really addressed, for a long time, but is something that needs to be addressed. The whole aspect of monitoring, error tracking, reporting, accounting, analytics. I mean, that's a microcosm in its own. In a big cluster, like I've been mentioning it before, with over 100,000 cores, I mean, every point in time, there is thousands and thousands of events happening. And keeping track of those, filtering out those which matter, and organizing the information such that you know what's going on, and you know what the status of the cluster is, and whether there is an issue, and where it is, and how to resolve it. You know, that is really an analytics challenge in its own right, and that's something we're working on. Now, a few things I would like to say where customers or end users can actually help themselves to be smarter about setting up the systems and run into less issues, less problematic scenarios. So my first here on slide number 11, I've entitled "Be Street Smart." So what I mean is, don't stand yourself in the way. Simplify wherever that's possible. This is sometimes hard organizationally speaking. I mean, if you are in a large organization, you have a number of projects or a number of departments which have conflicting interests. They all, fight for their share of the valuable resource, being the cluster. But making things simpler is sometimes, on the face of it, the best solution. If you try to accommodate everyone's wishes, then you basically end up in a giant conflict scenario. And there is really no way sometimes to resolve that cleanly. So my general advice is, in such situation, is really look at what are the most important goals, focus on them, and do your best then to satisfy the next level of goals, but always keep your eye on the most important goals. And if that is, for instance, to have high throughput and high utilization, then sometimes not really accommodating some of the other policies that you might want to have, that one of your end users wants to have implemented, is the best solution. Because if you look then at the data, how much throughput you got, how much utilization you got, you will see you're much better off than trying to be everybody's darling. On slide number 12, I'm basically saying think different. And let me give you a few examples what I mean. So one of our customers is running millions of jobs a day, and they really were running lots of small jobs. So the consequence was they definitely had throughput performance issues. And when analyzing the situation, it came down to the data persistency of our system. I mean, obviously, a system like Univa Grid Engine needs to persist status data out of all the jobs that get submitted, all the status changes that take place, all the cluster situation, all these things needs to be persisted out. And the classical ways of persisting out that data at some point run into a bottleneck as you scale out. That's just inevitable. So what these guys did, said, okay, let's try something completely different. So they went for a SSD RAID. So actually, it was a Fusion I/O system, which they were using for persistency. Now, a Fusion I/O system, you cannot easily fail over unless you have two, which is expensive, right? So they didn't. They simply were using backups, nightly backups, or whatever it was. And you might say, oh, okay, what happens if you actually, your cluster falls over, just before a backup? You lose a whole day. But, they were able to improve their performance by a factor of 2 or 3. And even if they have a failover situation, let's say 2 times a year, which is much, they actually don't have that. But even if they had that situation, I mean, they would lose 2 days. But on 363 days of the year, they have 2-3 times better performance. So, they can easily lose 2 or 3 days in compensation. I've mentioned array jobs. We still run into customers who have ideal situations for array jobs and are still not using them, and then suffer from performance problems because they have lots of jobs. So array jobs is a good solution for that. Also, if you have a chance, using more smaller jobs versus a few bigger jobs is the better choice. It's always challenging to find room for big jobs. I mean, it's kind of like you're trying to reserve a whole hotel in mid-vacation season for a conference. It's impossible, right? So on a busy cluster, it's very hard to make room for those large jobs. So splitting things up into smaller chunks is definitely much easier to manage if you have any chance to do that at all. And then also, usually customers shy away from preemptive jobs, meaning actually terminating them if a higher priority workload comes in, or if, for instance, one of those small jobs really needs to be squeezed in. So often customers shy away from doing that, but on the face of it, it sometimes is the better choice. So don't rule it out. That's really what I'm saying here. Another one of my pet peeves is to actually embrace and accept difference. So I've talked about the scenario where you have, for instance, some big jobs and lots of small jobs, and those things have conflicting policies usually, and it's sometimes very, very hard to get them aligned. So another way of handling the situation is actually, embrace it and make room in the cluster for the big jobs and the small jobs, meaning separate it out. You can do this by simply temporarily designate a part of the cluster, let's say for a big job, and then the rest for the small jobs. Or you make it a little bit more cleverly, meaning automate the whole thing, and that comes basically down to cloud sharing. So one of the things you could do is, for instance, break your cluster into two and let two Univa Grid Engine systems run on them. One is for the big jobs, one is for the small jobs. And then you have UniCloud, which actually can manage those two clusters and can look at them and say, okay, the cluster with the small jobs is currently not heavily loaded, but the cluster with the big jobs needs some more nodes. So I move a node over there from the small job cluster into the big job cluster. That's actually a very efficient way of handling things. It has two big advantages. First of all, it simplifies the configuration in either one of those clusters, and it provides total autonomy there. So, in the big cluster, you can do whatever you want to address the needs of the big cluster. In the small cluster, you can do likewise for the small jobs. What you should avoid, though, is what's called meta-scheduling, where you have also two clusters, but then a meta-scheduler sitting on top. Meta-scheduler meaning where the jobs really go through that meta-scheduler, and the meta-scheduler then determines should it be going to the left cluster or to the right cluster. The issue with that is, first of all, it adds a level of indirection to everything, to submission, to job control, to monitoring, to error tracking, to accounting, what have you. The second problem is if a job in principle can run on cluster A and cluster B, then cluster A and cluster B basically need to be configured to allow it to run. So you really win nothing. You have no autonomy. Those clusters really need to be looking the same. So what's the advantage? So that's why I'm really in favor of doing something like cloud sharing. Then my final advice is to use tailored solution as much as you can. By tailoring, I mean add-ons or things like scripting, customization, job classes, wrappers, portals, all those types of things which basically add an abstraction layer to the cluster and allow end users to go through these scripts or portals and address the cluster there instead of going there directly. If I look at our customers who have the least problems, then they usually are well equipped with portals, with submission scripts, using job classes, and similar things. So that allows them to control really how jobs get into the system. They can make sure that there is nothing being submitted that goes against the policies and similar things like that. It's much easier also for the end users to use the cluster. As opposed to that, if you have situations where you basically say to the end users, well, do whatever you like, you're really up for trouble. Because end users will, find ways of using the cluster that you have not planned, and they will cause you trouble. I mean, we see that basically every day. So using tailored solutions, using wrapping is definitely something that is worth considering. So with that, I'm actually already at conclusions. So what I would like to say is that workload and resource management systems are definitely more required than they ever were. I mean, with cluster sizes like we have them today, there's just nothing you can do without those systems. And definitely when those systems stand, then there's lots and lots of servers that produce nothing but heat, but definitely don't produce any output. So it is very crucial to have a robust workload management system in place. Specifically in the new era of cloud and big data, there is even more of a need because, for instance, big data let's spread out the usage of clusters of the classical outside of the classical HPC into farther-reaching areas like analytics and so on. If you use a workload management system of the type of Univa Grid Engine, then that allows you to benefit from more than 20 years of experience in workload orchestration, and you can move beyond that. As I've mentioned, there is a clear-cut set of challenges. Those are non-trivial. So if you want to address them, you have to build on best-in-class products, architectures, and also the development teams who know what to do with it. And then finally, being street smart about architecting the system, about configuring it, about managing it, about giving end users access to it is also an important thing, how you can help yourself for a better experience. So with that, I'm through with my presentation, and I'm sure you have something like a question.
I certainly do, Fritz. Thanks for that. It strikes me that the diversity, just going back to your slide there with the types of customers that you're working with, companies as different as pharma to a manufacturing, right? In the types of workloads. You guys just got done with kind of a road show. Maybe it's still going, but when you bring these users together of Grid Engine, do they have stories to share that can benefit each other in a typical, even though they're doing very different kinds of work? Do you see that?
Yeah, definitely. So,
Yeah.
first of all, our roadshow is more or less a permanent thing. We do these user forums, and we basically go to areas where lots of our customers or prospects are sitting.
Mm-hmm.
And sometimes you have situations like when you go to Houston, well, lots of oil and gas customers are attending, so
Sure.
they definitely can share. But even across different industries, there is best practices that you can apply. Let's say a life sciences customer running throughput is in no different situation, or a financial services customer is no different situations than EDA customer. There are certainly differences, with the applications and some of the workflows and stuff like that. But there's definitely best practices to share, no, not a doubt.
Yeah. And then the diversity of Univa's with Grid Engine being around for so long, you guys support all kinds of different architectures and everything from the x86 core to a PHY or a GPU and some other embedded type processors as well. Do you have a giant lab with all this gear with hundreds of thousands of cores at your beckon?
That would be nice.
Yeah.
Well, no. We have sufficient gear, though.
Yeah.
It's actually surprising how far you can get with, for instance, using container models.
Yeah.
You were from Sun, so you know the good old zones.
Yes. Of course.
Linux finally has something that is comparable with LXC or Docker. And so even, let's say, with 100 nodes, if you use lots of containers on them, you can get to staggering amounts of simulated nodes.
Mm-hmm.
And that gives you really a good test bed, for instance. Of course, we have systems with NVIDIA GPUs and with PHYs in them. We use things like Amazon, of course, for some of the testing that we do. So you have to be creative.
Sure. And then just from an architectural standpoint, I mean, does Grid Engine run on a single core somewhere and just has lots of little widgets running on each device that report to it, or is it more of a distributed kind of architecture?
So first of all, it is a distributed architecture, of course.
Yeah.
So you have what we call the execution daemon, which is our execution agent, and that runs on all of the nodes where execution is being done. Right now, that's also true for the host nodes, where a PHY or a NVIDIA GPU is plugged in.
Mm-hmm.
Although there is also talk about, at least for the PHY, to run a Grid Engine execd there. Then we have our central control unit, which is a parallelized node in itself. So it is a multi-threaded architecture to that end, and we're looking into even widening that space because, as I mentioned, there is all those scalability challenges, and at some point, even though the nodes get bigger and bigger, and nowadays they almost look like E25Ks,
Yeah, almost, sure.
and we're trying to make use of them, but there's definitely a need for spreading it out even broader.
Yeah. Well, kind of a wrap-up question here, Fritz. You started out something near and dear to my heart. It's the node count is kind of flat, but these cores are just going to keep increasing. What kind of advice do you have for customers? I mean, when you know that suddenly Knight's Corner will come around and suddenly there'll be 60 cores there or more, right? And that that might go up 5x in the same rack. How do they prepare for that? How do they deal with what's coming?
I think the major issue there is really the applications. I mean,
Yeah.
even today we have customers who buy those big core machines just for the memory, which is kind of absurd, right? You buy a 32 core machine, and then you may be using 8 because the application is just not using more, but you need all the memory.
Yes.
So I think customers should think real hard what makes sense for them. And then again, I think embracing the difference is an advice there as well. I mean, maybe you don't need all your cluster being equipped with the same type of nodes, right? Maybe for your applications, you split that a little bit and you put specific nodes which fit one application best in a part of them and other nodes in another part,
Yeah. Well, Fritz, this has been fascinating, and I'd like to thank you once again for coming on the show today.
You're welcome, and thanks for having me.
You
Rich.
bet. Okay, we'll see you at ISC.
Yeah, absolutely.
All right. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.